Well, hello everyone and welcome to your tutorial number 4 for the course CE 457A. We have two parts for this tutorial. In the first part, I'm going to walk you through an example. Then we're going to run that example and see the results of the algorithms for optimization. After that, part 2 begins, which is the genetic programming and explanation of some of the codes, some parts of the codes for the genetic programming. And after that, we will conclude this tutorial. Alright, let's get started. So the example is a supply and demand for vehicles. A dealership sells two types of vehicles, trucks and sedans, and needs to choose the prices that maximize their revenue. So in order to solve this problem, we need a mathematical model of the sales. Let's say that X is the price for a truck, and the price of a sedan is Y, and T and S are demands per month on trucks and sedans respectively. So we can formulate an equation like price demand equations will be something like this. Some arbitrary random values that somehow can make sense. After that, we need to assume that the dealership sells T trucks at a price of X dollars per truck and S sedans at a price of Y dollars per sedan. So we can reformulate that, formulate our revenue equation with something like this. R stands for revenue, TX plus SY gives us this new equation. So the optimization problem will be finding the values of X and Y such that the revenue achieves its maximal value. Now we can define this optimization problem as a minimization. So because we're going to maximize R, maximizing R is actually equal to minimizing negative of R. So after that, we can use the first order optimality condition and find X and Y that minimize negative R or maximize R, the revenue value. So we have an X star, which is a local minimizer for differentiable function. Then we can say the gradient of this function at this point is equal to 0. So our function for minimizing is negative of the revenue equation. And here, those points, or that optimal or local minimizer, is a vector of X and Y. So here, X dollar per truck or Y dollars per sedan. Using this gradient, we can take the partial derivatives of this function with respect to X and Y. So the partial derivative of negative R R with respect to X is this equation, and the partial derivative of F with respect to Y is this equation. So because we're setting them equal to 0, it doesn't matter if you're considering this negative sign or not. The answer will be the same. And after solving that system of equations, we obtained that X is 15,500 for a truck, and Y is $13,000 for a sedan, and that will be the revenue. Now we want to go through the codes and solve this optimization problem using the previous algorithms that we went through. Also, please note that I took this example from this reference. All right. So I define my revenue function here as a new cost function. And for this specific sample, the length of the x must be equal to 2. Otherwise, we need to raise a value error. This is the revenue formula. And this is a cost function, negative of r. And we're returning the cost function that we are going to minimize. Okay. Then here I have lf_config cost function revenue. So the range can be something that makes sense because the optimal values are like 15,000 or 13,000. So we need to specify the range in a way that somehow makes sense. You can play with that to see what results you get with different algorithms. Also, I typed something here that for this specific cost function, we need number of trucks. Actually, it's not true. This is the cost of trucks and cost of sedans per dollar. Yes. All right. The first algorithm, let's try local search with 500 iterations and a convergence threshold of 0.01. The cost function is revenue. Let's run that. I think this algorithm actually has stuck in a local minimum. So here we have 12,000 and 10,000, while we need 15,000 and 30. So, yeah. Let's move on to the next algorithm, or maybe just to create a convergence threshold. Let's see what we get. Okay, the situation got worse. It's not a good solution. Let's try iterative local search. Mm, 2,200. I think this one's good. Save it. Okay. Somewhere around here, this is our best solution. While we were looking for 15,000, somewhere around here, and 13. So that will be somewhere around here. Yes, 18,000 and 15,000. Let's use another algorithm, for example, PSO. And let's leave, actually here, let's leave them as they are. So we had 15,000 here, and yes, the solution must be somewhere around here, like this point. Let's use genetic algorithm. I think it actually did a great job compared with the previous algorithms. Yes, so these values are very close to the ones that we're looking for, like 15,500 and 30,000. So we can say that genetic algorithm performed way better than the previous algorithms. Okay, this is from this example, and now let's move on to, let me close this, we don't need this anymore. GP, genetic programming. So we have different files for that. We have a new config file for GP and a new main file. So for genetic programming, we're actually using deep distributed evolutionary algorithms in Python. You can use these two links to read actual documentation for genetic programming with deep. So what is deep? Well, as they mentioned on their website, deep is a novel evolutionary computation framework for rapid prototyping and testing of ideas. Because it's way easier, we're going to use deep and GP, genetic programming module, and write down the code for genetic programming. You also need to install deep as well, pip install deep. And we have our config file. And I will walk you through these variables as well. All right, so we need some functions. The first one is the create random dataset. So as you know, for genetic programming, we need a dataset. So a dataset has some features and a target value. We have samples or data points, and each sample actually has some features. For example, here x1, x2, x3, x4, or x0, x1, x2, and x3. These are our features, and this one is the target value of that sample, that specific sample. So in this code, we're generating a random data set using this formula, and after that, we're adding some noise to that. We're also using a seed of 42, so the results will be always the same. Then we have a deep genetic programming function. We're creating deep types for fitness and individuals. For example, in this line of code, weights represent, actually they're used in fitness comparison, so the negative value corresponds to the minimization problem. This is a ready-to-use single objective that minimizes a fitness function named fitness mean. Then we need to define our primitive set that actually contains all the possible mathematical operators. So as you know, in genetic programming, that tree represents a function. So here we are going simple. We're only using addition, subtraction, multiplication, and division. You can add more, like sine, cosine, logarithm, or other functions. Then let's move on to line 24. Line 23, define the primitive set with only mathematical operations. As mentioned before, we're defining our primitive set here. Arity equal to the number of dimensions. So GP module provides methods and classes to perform genetic programming with deep. So we're using those methods and classes in GP. Then we're defining the mathematical operations, for example, addition, subtraction, multiplication, and division as defined here in the config file. And also note that this arity is the number of arguments or operands that a function or operator takes. So if we were to choose sine or cosine, this arity would be 1. Because only one parameter or only one operand did they take. Next part, define the evaluation function. So for the evaluation, we are getting MSE as the fitness function. And here in the we're using the compile, I think it's module method in the GP module in order to compile primitive set against the individuals. So it returns the results produced by evaluating the tree. We need to evaluate each tree to see like the output of which one is closer to the target value. Replace variables in the expression using the mapping, and we're calculating MSE. The next important part is to create a toolbox for genetic programming operations. So we're using the toolbox. I think it's the a class in GP. So we're using toolbox, or actually a module base. Yes, I think it's a class in base module in deep. So we're creating a toolbox for genetic programming operations. A toolbox is used to register various operations that will be used during the process, that evolutionary process, like when we create individuals or select parents or mutate them and evaluate their fitnesses, mutation, crossover, those processes. So it used to register various operations for those processes. Line 55 and line 57 are the same, so pure if the max expression depth is not none, we're using that. And in case it was none, we would use 3 as the maximum expression depth. Then after that, it registers an expression generator using this function, gen half and half. This means that the generated expression will have a maximum depth as is specified by this variable, like the depth that a tree will have. Okay, I'm not gonna go deep through these lines of code. Maybe like the individual, population, compiler, all are obvious what they're doing, and you can also go to documentation and read this documentation text. Also, the code is very well commented, so you should have no problem. You can refer to these two links for the documentation. Then we move on to the format expression. This format expression function actually outputs the function, the best tree in shape of a human readable format. So here we're showing show the addition with this symbol, show the subtraction with this symbol, multiplication, and trueDiv like this. And we're also using trueDiv because it handles the division by 0. So it's important that you use trueDiv, not other predefined divisions. Then we move on to main genetic programming. The function takes the values. We have number of samples. So the number of samples is related to the dataset. The dataset has 100 samples. And number of dimensions. So dimensions is 5. For example, we consider that the dataset has 100 rows and 5 columns. 4 columns for the features, and the last column, the 5th one, for the target value corresponding to each feature in the sample. Then we have the functions like addition, subtraction. You can add more. If you add more, you need to define. You need to modify this part. Then population, number of trees to generate, 300. Here we have 300 as well. Number of iterations, which is the same as I mentioned in genetic algorithm. Number of iterations and number of generations are the same. Crossover probability, mutation probability, and maximum expression depth, like the height of the tree. So here we're creating our data set. Then we're using that toolbox. Make the modules in deep library. Deep genetic programming. After that, we're creating the population using that toolbox. Then we're going to evaluate the entire population, performing the evolutionary loop. So here we have crossover probability, mutation probability, and number of generations. Here, select the next generation individuals. We're generating the offsprings for the next generation. Here, clone is used to make sure that genetic operations are applied to the copies, not the originals. Then we move on to crossover and mutation. So we produce a random value between 0 and 1, and if that value is less than crossover probability, we create a new individual by mating the previous childs together, and then those childs need re-evaluation. Then we need to move on to mutation. Then we generate again a value between 0 and 1, and if that value is less than the mutation probability, we will mutate that offspring. Then we need to evaluate the offspring individuals and replace the old population by the offspring. All right, let's run the code. As you can see, the cost function is constantly decreasing. Well, we plateaued here, but it's decreasing, and after 10 generations, this is the best individual found. arg1 plus arg2 plus arg0. Then again, we have another plus arg0. Like we can say 2 arg0 plus arg1 multiplied by arg3. So here arg1 is like x1. The second feature, arg0 is the first feature, arg3 is the fourth feature. So there's no sign of the third feature. We can actually interpret this as 2x1 plus 2x0 plus x1 multiplied by x3. So it says that this is actually the best function that can represent this function. Here we had 3x1, 2x0, negative x2, and 1/2 x3. So after 10 generations, this is the with these operations, this is the best function that can fit. We can fit this data, the generated samples, that can represent. Where is it? This function. Let's change some values here. And population maybe 400. Okay. All right. So we actually got better results here. The cost function is, yes, it's less than this one before. So for example, we have x0 multiplied by x1 multiplied by x2 minus x2 multiplied by x2, like x to the power of 2, plus or maybe minus x1 plus x0, 2x0 plus x1, or plus 2x1. Yeah. This is another function that can represent that function after 20 generations and with such a low cost function. Alright everyone, I think that's it for today's tutorial, and this concludes the 4th tutorial. Goodbye.